everything we call real is made of things that cannot be regarded as real. If you've ever looked at a photo of the universe with billions of shimmering galaxies, you probably thought about its infinite expanse. Our attention is often drawn to the enormous, because that is the world we inhabit, where things follow simple, understandable laws. But what if we did the opposite? Instead of zooming out, we zoom inward, shrinking down from the body to the cell, from the cell to the molecule, from the molecule to the atom. We would encounter another world, one so minuscule that imagination struggles to grasp it. And precisely in that world, the familiar rules of classical physics dissolve, giving way to a bizarre and mysterious set of laws we call quantum mechanics. We tend to believe that everything is predictable. A ball thrown into the air will fall along a determined trajectory. A car traveling at a constant speed will arrive at its destination at the calculated time. But at the scale of atoms and particles, those laws no longer hold true. An electron can be here, but also simultaneously there. A particle of light, a photon, can behave like a particle, but then instantly spread out like a wave. Seemingly contradictory, yet that is the very essence of the microscopic world. Quantum mechanics is not just a physical theory. It's an entirely new lens through which to view the universe. By understanding it, we don't just understand tiny particles, but the very foundation of the cosmos, from massive stars to our own existence. The famous Double-Slit experiment revealed this mystery most clearly. When a beam of minuscule particles, such as electrons, is fired through two narrow slits, if we don't observe them, they create an interference pattern, just like water waves. This indicates that each particle, even when fired individually, seems to pass through both slits at once and interfere with itself, behaving like a wave. But when we place a detector to observe which slit each particle passes through, the interference pattern vanishes. Instead, they suddenly choose to pass through a single slit, behaving like rigid little marbles. It seems the particle's behavior depends on whether or not we are observing it. This raises a profound question. Are we merely passive observers? Or are we an active part of the quantum drama, where our act of witnessing influences reality itself? Imagine a particle of matter as a probability cloud. It doesn't have a fixed location. Rather, it can only be described by the probability of where it might appear. Instead of saying an electron is here, we must say, there's a 70% chance it's here, a 20% chance it's there, and a 10% chance somewhere else. When we measure it, that cloud instantly collapses into a specific point, as if the universe is forced to choose a single outcome. But moments later, the particle returns to its ambiguous state. Quantum mechanics teaches us that absolute certainty is an illusion. The microscopic world does not exist as rigid building blocks, but as continuously fluctuating possibilities. The first hint that this strange world existed came from the study of heat and light. Back at the turn of the 20th century, scientists were baffled by how hot objects emitted light. The physics of the time predicted that an object should radiate an infinite amount of energy, an obvious absurdity. It took a quiet revolution, started by a brilliant mind, to propose a solution. Energy wasn't continuous, like a ramp, but came in tiny, discrete packets, like tiny steps. These packets were called quanta. this seemingly small idea fundamentally changed everything. It introduced the concept of energy quantization, tearing down the continuous, clockwork universe view. This idea later paved the way for others to realize that matter, too, behaved in these discrete, probabilistic steps. One of the strangest concepts is quantum entanglement. When two particles are created together, their states become so tightly linked that even when separated by billions of kilometers, if we measure the state of one particle, we instantly know the state of the other. It is as if an invisible thread connects them across space and time. Some have called it spooky action at a distance, because it challenges the very limit of the speed of light, suggesting a connection that defies our normal perception of locality. Nevertheless, modern experiments have proven entanglement to be real. This instantaneous link is not magic. It's a profound feature of the quantum fabric. And this very phenomenon is becoming the foundation for future technologies like quantum computers and hypersecure communication. Conventional computing relies on bits that are either 0 or 1. Quantum computers use qubits, which can exist in a superposition of both the 0 and 1 states simultaneously. This ability to exist in multiple states at once is what gives quantum computing its colossal power. With just a few hundred stable qubits, a quantum machine could perform calculations involving more variables than there are atoms in the observable universe. This means solving problems that are currently impossible, simulating complex molecular interactions for new drug discovery, creating perfect catalysts for clean energy, breaking currently unbreakable encryption codes, and optimizing global logistics networks far beyond anything classical computers can manage. The quantum era promises to solve humanity's most complex problems. However, building these machines is perhaps the greatest engineering challenge in human history. To maintain the fragile quantum states, superposition and entanglement, qubits must be isolated almost entirely from the environment, and this means operating them at temperatures near absolute zero, colder than deep space, or isolating them in extreme vacuums. Even a stray vibration, a tiny fluctuation in temperature, or an unwanted electromagnetic wave can cause the quantum state to instantly decohere, collapsing the superposition and turning the powerful qubit back into a simple, error-prone classical bit. Scientists are racing to find ways to manage this quantum fragility, developing highly sophisticated quantum error correction codes and exploring exotic qubit technologies, from superconducting circuits to trapped ions and topological qubits. The current challenge isn't just scaling up the number of qubits, but increasing their coherence, time, how long they can hold on to their quantum magic before the environment interferes. This technological battle is what defines the cutting edge of the quantum race today. Yet, behind the promise of technology, quantum mechanics still poses profound philosophical questions. For instance, if a particle exists only as a probability until observed, does reality require consciousness to exist? Or does it exist independently, and are we merely late discoverers? The famous Copenhagen interpretation, championed by Bohr, suggests that the act of measurement is what forces the wave function to collapse, bringing the quantum world into classical existence. But this isn't the only answer. The many worlds interpretation offers a startling alternative. It suggests that the wave function never truly collapses. Instead, every time a measurement is made, every time a quantum choice occurs, like the electron deciding which slit to go through, the universe instantly splits into separate, non-communicating parallel universes, one for each possible outcome. In one universe, the electron went left. In another, the electron went right. If this interpretation is true, then right now, countless versions of you exist in infinite parallel realities, living out every possible outcome of every decision you've ever faced. This moves the mystery from the nature of the particle to the nature of reality itself, turning the uncertainty principle into a cosmic branching tree. If we look back at history, many great inventions stemmed from understanding and applying quantum phenomena. Lasers, transistors, computer chips, GPS technology, all rely on knowledge of the particle world. Thus, no matter how unbelievable it may seem, quantum mechanics is not just abstract theory, but the foundation of modern life. Every time you turn on your phone or watch TV, you are directly utilizing the achievements of the quantum world. This proves that the bizarre fluctuations at the atomic scale truly shape the reality we live in. Another fascinating aspect is wave-particle duality. Light, which we see every day, can be viewed as a stream of particles or as a wave. This is reminiscent of music. A song is both a sound wave traveling through the air and a specific sequence of notes on the sheet music. And perhaps the universe is a quantum symphony where particles and waves are not separate, but merged in an endless dance. In the quantum world, a particle can tunnel through a barrier that is classically impossible, a phenomenon called quantum tunneling. It is this very effect that allows the sun to shine through nuclear fusion, because without it, the particles would never have enough energy to fuse. Thus, every sunrise we witness is a direct result of the quantum miracles constantly occurring in the core of stars. So, why should we care about this incomprehensible, microscopic world? Because it's not just about invisible particles, but about the very nature of reality. We often believe in certainty, that the chair we sit on is solid, but quantum mechanics reminds us that everything is based on probability. The chair is a collection of countless vibrating particles. Reality, it turns out, is more fragile than we imagined. But it is in this very fragility that the universe's beauty lies. From uncertainty, myriad possibilities can emerge. It has been said that quantum mechanics is like a poem of the universe, written in the language of probability. We cannot read it like a logic textbook, but we can feel the rhythm hidden within. And if we open our hearts, we will see that the smallest reflects the largest. The world of particles is not just the foundation for matter, but also a mirror for us to reflect on timeless questions. Who are we? Where do we come from? And what is the ultimate meaning of this reality? When you look at an atom, it is mostly empty space. The nucleus at the center is so small that if you magnified it to the size of a golf ball, the electrons would orbit at the distance of an entire stadium. That means the solid matter around us is predominantly void. This makes us ask, what holds them together? And the answer lies in invisible quantum fields, the fundamental forces that bind particle to particle. Thus, what we call solid is actually just an illusion created by these oscillating fields. Once again, we see that the universe is not a rigid block of matter, but a symphony of energy. As scientists continue to delve deeper, they realize that all fundamental particles can be described as excitations of underlying quantum fields. Quantum field theory suggests that the universe is a sea of energy fields, and particles are merely localized excitations in that sea, like ripples appearing on the water's surface, which then dissipate, but the pond itself remains. If this is true, then all of us are merely temporary fluctuations in a much larger, invisible substrate. This is both scientific and philosophical, as it suggests a deep sense of connection between everything. And that is everything we can say about the quantum world, a world both distant and astoundingly close. Hopefully, from now on, every time you look at familiar things like your phone screen or a light bulb, you will see the hidden marvel within. Because quantum mechanics is not just an abstract theory, but the foundation of modern life itself. Remember that everything begins with the smallest and most uncertain things. If one electron can exist in multiple states simultaneously, then why can't we open ourselves up to the countless possibilities within ourselves? Thank you for joining us on this journey of discovery. If you found this fascinating, don't forget to leave a comment and share this video with your friends. Be sure to hit the like button and subscribe so we can continue exploring this wondrous universe together.